Binomial distributions. Binomial experiments are experiments having all four of these conditions. And the first condition is each observation falls into one of two categories. We call them success or failure. So success isn't necessarily a positive. And I just want to emphasize that in order for us to have a binomial experiment, it only has two possible outcomes. So in this example, we have an experiment and they're concerned with the number of people who gets colds after being doused with water on a winter day. Success might be defined as getting a cold. So it's not necessarily a positive, but we're looking to do an experiment to see if being doused with water would give us a cold. So the experiment, or the binomial experiment in this case, success would be they got a cold, and failure would be they didn't get a cold. So it's one of two possible outcomes. The next condition is it's a fixed number of observations. So a fixed number of observations, and we're going to label it with n, that is a key thing in order to do a binomial experiment. And with those n observations, they must be independent of each other. So knowing the results of one observation tells us nothing about the other observations. And then lastly, the probability of success P is the same for each observation. So probabilities will not change. Here's the notation for binomial experiments. When we're talking about the number of times a trial is repeated, we'll use the lowercase n. When we're talking about the probability of success in a single trial, we'll use the lowercase p. And again, that's probability for success. When we're talking about the probability for failure in a single trial, we'll be using the lowercase q to represent the probability of failure. Now, in order to find the probability of failure, or q, we will need to take the value of p and subtract it from 1. So remember, when we're working with probabilities, a probability is always a value between 0 and 1, and the complement of the 1 probability will equal 1 minus the probability. And then lastly, the random variables will be represented with a lowercase x. And it will always start with the random variable of 0. And it will go up to the number of trials that we have repeated. So it will go up to the number n. So here's an example. We're asked to decide whether the experiment is binomial experiment. And if it is, it wants us to specify the value of our n, the number of trials, our p, which is the probability of success, our q, our probability of failure, and then all the possible values of our random variable x. So we're going to be doing this for this example, which is a certain surgical procedure has an 85% chance of success. The doctor performs the procedure on 8 patients. The random variables represent the number of successes in the trial. So we're going to go through our checklist to see if it's a binomial distribution. And the first is each observation falls into a success or fail? And in this case, because we're asked the surgery or the certain surgery procedure has an 85% of success, well, then we know that we have 85% of success, and then the failure would be the surgery was not a success. The next condition is, does it fit into a fixed number of observations? And in this case, it does, because the procedure is done for 8 patients. So that's a fixed number of observations. Then the observations are independent of each other. And they are independent of each other because it doesn't matter what happens to the first patient, and it doesn't change the probability for the second patient of having success. And then lastly, the probability of success is the same for each observation. So yes, the probability of success, that 85% chance, is the same for each patient. So now we can identify our N, and our N is the 8 patients that were observed. So that would be the trial number. And then our percentage of success is that 85% chance of success, and then we need to find the Q by taking 1 minus P. So in this case, we get our Q value is that 0.15, or the probability of failure. And then lastly, our random variables for this trial will be 0 through 8. So these are the random variables that we will be working with. This next example, again, we're doing the same thing. We want to find if it's a binomial experiment, and if it is, we're going to name the N, P, Q, and our random variables. We have a jar that contains 5 red marbles, 9 blue marbles, and 6 green marbles. You're randomly selecting 3 marbles from the jar without replacement, and the random variable represents the number of red marbles. Now here's the key information here. Without replacement, remember, if we're not putting the marble back in the jar, it changes the probability. And because the probability is being changed, this would not be a binomial experiment. So it's not going to be the marble's not replaced, the probability will change. Therefore, each probability is not independent of each other, and it would not be a binomial experiment. Pause and try. So this is a binomial experiment. It's either a fail or success. We have a 41% chance of women in the United States consider reading as their favorite leisure time. So that would be our probability of success, which is our P. And then the Q is 1 minus 0.41, and we get 0.59. And then all our random variables. Remember, you always have to start with 0, and it goes all the way up to our trial observation, which is 4. Pause and try. So in this case, it's not a binomial experiment because the probability is not the same for each trial. Pause and try. This is a binomial distribution, and again, our N is 12. Our probability of success is 0.68. Failure is 0.32, and our random variables go from 0 to 12. So now when we're looking at the binomial probability and finding the actual probability, we would be using this formula. And the formula is the probability, and it uses the combination formula and the percent of fail and the percent of success. So notice here, when we're doing this, we need the trial size, the number of trials, the probability of success, our probability of failure, and the number of successes in the trial. Note that the failure is N minus Q, that exponent for the Q value. Now we will be doing this in the calculator, so we will not be actually doing that formula manually. Our calculator has the ability to find the values for us. So if you have a Texas Instrument 83 or 84, we're going to be using that to find the binomial probability. So we're going to use it for this example. A microfractured knee surgery has a 75% chance of success on patients with degenerate knees. The surgery is performed on 3 patients. Find the probability the surgery being successful on exactly 2 patients. So in order to do this, we're going to first identify the trial size, the percentage of success, our Q value, which is the percentage of failure, and we want our random variables. So there's 3 patients in the trial. That'll be our N. The probability of success is that 0.175, and then our probability of failure would be 1 minus 0.75, which would be 0.25. Or the random variable we're looking for is exactly 2, so therefore the random variable would be 2. Now we're going to use the calculator, and to do that, if you have an 83, 84 above, you need to go to your second key and VARs, which is that distribution menu. So you see the DISTR above the VARs button. We're looking to get into that menu. You're going to need to arrow down to the binomial BINOM PDF, and that will get us the binomial distribution information. So on some calculators it's choice A. It could be different in your calculator, so you want to make sure you're choosing the right option. Then you're going to hit enter. And when you hit enter, if you have a newer calculator, you'll have this screen where it has trial, and it'll have the P, and it'll have the X value, and then you can hit enter. If you have an older calculator, you're going to need to put in the N and then a comma, put in the percentage of success, another comma, and then the random variable probability you're looking for. Once you enter in that information, you'll enter and you'll get your probability information. So in this example, the probability would be 0.421875, and again you'll round it based on what you're asked for. Pause and try. So this one would be approximately 0.251. So the probability of 5 U.S. adults trusting national newspapers to present the news fairly and accurately is 25.1%. Pause and try. So the key information here is what is our percent of success? And because it's a true or false test, it's a 50% chance. So you had to find that information in this before you could go any further. And once you find that, then you can find the probability of exactly 7 correct answers. And that would be 0.193. And the probability of 7 correct answers is 19.3%. So let's do an example here of how to create a binomial distribution table. So in a survey, American workers and retirees are asked to name their expected source of retirement income. 36% of American workers expect to rely on Social Security income. Randomly selecting 7 workers to participate in this survey are asked whether they expect to rely on Social Security for their retirement income. So now we want to create a binomial distribution for the number of workers who responded yes. So the first thing I want to do is I want to pull out the information, the N value, the total number of trials, which was 7, and then our probability of success, which was given, which was that 36% or 0.36. And then our Q value is 0.64, and all our random variables are 0, 1, 2, 3, 4, 5, 6, and 7. So now we're going to do the distribution or find the probability by first starting with the 0. So we're going to use the Texas Instrument calculator, the 83, 84 above. You're going to go to the second VARs menu again, and you're going to choose the binomial distribution, the PDF, and you're going to enter in 7. You're going to enter in the 0.36 for our probability of success, and we're going to start with 0. we're going to find that probability and we're going to start filling it in to our probability distribution table. So you want to start off with your random variables going from 0 to 7, and then you're going to find each probability by doing this procedure. So we find our first probability to be 0.044. Now, to repeat this process without having to enter in all the data again, you can use your second entry key, and the second entry will pull up the last entry in your calculator. And then all you need to do is arrow over to the 0 and change it to 1, and then you will get the next probability when you hit enter. So you'll get the next probability, in this case would be 0.173. And you can continue to do that to fill out the table of probabilities for each random variable. And then you will have your probability distribution. One key note that I want to emphasize here is when you're doing the calculator and you have that capital E with a negative number, a negative 4 maybe, that means that you have scientific notation, and whatever that negative exponent is means you need to take that decimal place and move it over to the left that many times to get the actual decimal. Because sometimes the decimals are so small that it can't be read in the calculator and it needs to give you scientific notation. So that is very important when you're doing binomial distributions, to recognize what the calculator is showing you. Pause and try. So if you created the binomial distribution for the random variables from 0 to 7, it should look something like this. And again, be really careful when you have that negative exponent to move the decimal place over the number that the negative number is. So when we're doing binomial distribution and we have certain information given and they're asking us for a probability of at least 2, we need to sum up the probabilities. So the first thing you want to do is find the information we're looking for. So we have a survey that indicates that 41% of women in the United States consider reading their favorite leisure time activity. And they're randomly selecting 4 women, and they're asking if reading is their favorite leisure activity. To find the probability at least 2 of them responded yes. So when we're doing this, the key information here is they want us to round 3 decimals. So I'm going to pull out the information I need, which is the sample size, which is 4, my probability of success, the 0.41, and then my random variables go from 0 to 4. Because it's asking for at least 2, that means that I need 2 or more. At least means it includes 2, but it wants every number above that. So that means I have to find the probability of 2, of 3, and of 4, and then add them together. So when you do this, you're finding the probability of 2, the probability of 3, and the probability of 4. You take those probabilities and you add them together to find the probability of at least 2 responding yes. So when you get this, you should get something like 0.542. So when you have it on an interval, you're going to have to do some addition. Pause and try. So this is at least 6. So our n value was 9 here. Our probability of success was 0.60. And when you found your probabilities, you sum them up, you should have gotten 0.482. So if you were asked what is the probability of at least 6 U.S. adults trusting the national newspaper to present news fairly and accurate, you would say 48.2%. Pause and try. So again, I'm pulling out the information. It's the same from the previous exercise, except for it wants less than 4, which means it's not including 4. But don't forget the 0. When you add these probabilities together, you get 0.099. So you would get a probability of 9.9%. Pause and try. So in this one, you had to find the probability of success. And when we're talking about a multiple choice question with 4 possible answers, the probability of success is 25%. So that's key information when you're doing this particular problem. And then it's asking 7 correct answers, so you need 7 and above. And you find those probabilities when you sum them up. It's a probability of 0.0034 or 0.34%. Very low chance. Pause and try. So you're pulling out the information. Our sample size is n, or our trials is n, and the percentage of success is 51. So exactly 2 would be 0.039. It says more than 2, which means it's not including 2, so it's every number above 2, would be 0.952. And then between 2 and 5 inclusive means that it's also including 2 and 5. So when you sum up those probabilities, you should get 0.59. This next part for binomial distribution is finding our mean, our variance, and our standard deviation. Well, when we're finding the mean for a binomial distribution, you simply multiply the number of trials times the probability of success. That will be our mean. Our variance is multiplying the trial size times the probability of success times the probability of failure. And then the standard deviation, you'll simply square root the variance number. So let's see what this looks like. In Pittsburgh, Pennsylvania, about 56% of the days in the year are cloudy. Find the mean, variance, and standard deviation for the number of cloudy days during the month of June. And it's asking us to round to the nearest tenth. So because the month of June has 30 days in it, the trial size in this case would be 30. Our percentage of success was given as 56% or 0.56. And the percentage of failure, again, 1 minus 0.56 would be 0.44. So to find our mean, we're taking the n value times the percentage of success. So we get 30 times 0.56 would equal 16.8. Our variance is the n times the p times the q, and we would get approximately 7.4. And then to find the standard deviation, you would square root the value of this variance, and you would get approximately 2.7. Pause and try. So in this case, our n value is 7, p is 0.59, and your q is 0.41. So you should have gotten your mean is 4.1, the variance, is 1.7, and the standard deviation is 1.3. Pause and try. So our n is 5. Our probability of success is 0.11, and our Q is 0.89. So you should have gotten your standard your mean is 0.6, our standard deviation or variance is 0.5, and the standard deviation is 7.